Okay, this is section 2.5, linear and non-linear relations. So we did touch upon this yesterday. There's a bunch of different questions about what constitutes a linear relation and what constitutes something that's non-linear. So we're going to talk about that today. So here we have two graphs. These graphs are called growth charts. Doctors use them to help judge the health of young children. The graphs show the normal range of lengths for boys and girls from birth to age 3. Okay, so here's our age in months. So 3 times 12 is 36. So there's our 3-year-olds, and there's our 4-month-olds. So this tells us how long approximately they should be, or what percentage they should be in. Okay, a linear relation, it's a relation between two variables down here. It's a relation between two variables that forms a straight line when graphed. So examples of linear relation could be something like that, could be something like that, right? Okay, it's a straight line. How do linear and nonlinear graphs compare? Use the growth charts to answer the following questions. What is the same about the growth of the young girls and of the growth of the young boys? So here, these are boys, and these are girls. What's the same about them? Who can tell me? Yeah, Nicholas.
The starting measurements.
Yep, that's right. Yeah, the starting measurements. Good. What else can we generalize? Yeah, Tyler?
You could say that they're both growing. So
Yeah, you can say that they both have an upward trend. Christian?
They both seem to be increasing at the relatively same rate.
Okay, good. Yeah. How does the growth of young girls differ from that of young boys? Yeah, Adam.
The girls seem to, at around a year, seem to be growing a little bit slower than the boys.
Yeah, I would say even before that, right? Even here, this part of the graph is moving upwards quicker than this part of the graph, right? Can you see that? There is a slight difference on that slope. You guys see that? Okay, so the young boys are growing quicker. The graph of a linear relation forms a straight line. For what age range does the growth of girls and boys appear to be linear? What do you guys think? Henry. Looking up here, what do you think, which part does it appear linear? So here it's not, right? Because you're curving, right? It's not a straight line. What about from, say, here on, Henry?
yeah, it's like more straight.
Yeah, more straight. Linear, yes. Good. So do you see that? So probably from about maybe just after, maybe 16 months or so, it appears linear. Okay? So there's this big jump in growth at the beginning, and then it slows down, and it's pretty consistent after that. Make sense? Okay, for what age range does the growth of girls and boys appear to be nonlinear? So again, if this part is linear, this part would be nonlinear, right? Linear. Linear. Any questions about that? What's the difference between linear and nonlinear? Matthew, at the back, what's the difference?
Linear, it's an increase, and in nonlinear, basically it's turning into linear.
No. Linear could be a decrease. Could be. In this graph, you're right, but what's the main difference between nonlinear and linear, not specific to this graph?
Like the trend is showing.
It's right here. It's a straight line. That's what we're looking for, okay? It's linear, it just means it's going straight, okay? If it's curved, Matthew, you know the difference, right, between a curve and a straight line, right? This is curved, right? This is curved, exaggerating it, and that's a straight line, okay? That's what you need to know. How do changes in nonlinear graphs differ from changes in linear graphs? Sorry. What's the difference between nonlinear and linear graphs, the changes? How do they differ? So when we're talking about the changes, we're talking about those y values. Robert?
Since linear graph is a straight line,
Yeah,
it has to increase by the same rate all the time since it's straight. But with a non-linear graph, since there's like a curvature,
yep.
The rate of the increase can be, or decrease can be different because it's like an arc, it's not directly straight.
I hope everyone was listening. Perfect answer. Perfect, okay? Very good. Yes. It's exactly what I was looking for. It's the rate of increase. In the linear, it's increasing consistently the same. Each time it moves over an x, it moves the same amount in y. Or it could be moving a different amount, but that amount is consistent. Okay? Whereas nonlinear, it's not consistent. It could be different, it could be less, or it could be more. All right, Steven.
Often you can use a linear relation to model data on a scatter plot. This linear relation corresponds to a line of best fit. Lines of best fit pass through or close to as many points as possible. Any points that are not on the line of best fit should be distributed evenly above and below it. A line of best fit can help you make interpolations and extrapolations. Many nonlinear relations can be modeled with a curve of best fit. You can draw curves of best fit using the same method as for a line of best fit. A curve of best fit should pass through or close to as many points as possible, and any points that are not on the curve should be distributed evenly above and below it.
Good. Line of best fit. It's a straight line that comes closest to the points on a scatter plot. A curve of best fit, it's a curve, comes closest to the points on a scatter plot. Is this new for anybody? Hands up if you've never heard of. Okay. Okay, good. I wasn't sure. I'm not sure if you guys have done this in science or not. No? Okay. Okay. So you will see this again, though, throughout high school and science as well. So this, I got to kind of determine here if I'm going to draw a line of best fit or a curve of best fit. What would you guys think? Right? Because I could draw like that, or I could draw a straight line. What do you think? Who has an opinion? Oh, it's not on? Sorry. Sorry, here's our example one. Use a line of best fit. Oh, sorry, it tells us in the title. So here I could try to draw like a curve of best fit, but there's no data points down here, so I cannot do that. So the best I can do is a line of best fit. Okay, so here I have approximately, again, you're never going to have the exact same answer, but I have approximately the same amount of points on top as on the bottom. Justin?
Sir, for a curve of best fit, do you need to have points at the beginning area?
Yes, there would have had to have been points over here. We'll see that in the next example. Tyler?
Does it all depend on where your points are? So like if your points that are plotted on the graph to create a sort of like curve shape, like what Justin was saying on the bottom?
Yes.
you would put a
Right.
curve of best fit.
And we'll see that in a minute. Okay, so this is a gymnophlamid lizard. Never heard of that word. Gymnophlamid. Anybody know that word? Probably saying it wrong. Gymnophlamid? Gymnophthalmid. Lizard lives in the Amazon rainforest. Recent research found that this lizard keeps its body temperature close to the temperature of its surroundings. The table lists data from this research. So again, we have temperature and the lizard's body temperature. Okay, here's an interesting one. Both measured, both the same units. Which one's dependent and which one's independent? Everybody should know this, right? Think about it. Luca.
Surrounding temperature is independent and the lizard's body temperature is dependent.
Right, because the Earth or the sun is not changing its temperature based on what the lizard's doing. It's the other way around, right? If it's hot out, the lizard is going to change its temperature. Okay, so the lizard's body temperature therefore would go on the y-axis. Okay, so this is one of those scenarios where even though they're the same units and they're both measured, it's still quite clear which one's dependent and which one's independent. Okay, it says graph the table. Here's our graph down here. How are two variables related? Is this relationship linear or nonlinear? I would say it's linear because there's my line of best fit. If it was a curve of best fit, it would be nonlinear. But again, there's no points down here, so I can't draw any line there. My line has to start somewhere up here. and it goes straight through the data points. Okay? Really can't draw much off from this. Okay? You guys might draw, a line, something like that. But again, this line here has way too many points on the bottom. So we're all going to be, even though not exactly the same, we should be close, very close to this, right? How are the two variables related? Is this really, oh, sorry, we answered that. C, draw a line of best fit. We did that. Estimate the lizard's body temperature if the surrounding temperature is 26 degrees. So what are we going to do? 26 degrees. We're going to go up, find our line of best fit, and then go over. So I would say 28 and a half almost. 28.4 maybe. Okay? So he has a temperature 28.4 when the surrounding temperature is 26. Estimate the lizard's temperature if the surrounding temperature is 35. So what do we have to do now? What's it called? What's it called, Matthew, in the front?
Extrapolate.
Yes, extrapolate. We got to go up to 35, right? Which is going to be somewhere 31, 32, 33, 34, 35. Somewhere over here. Way off the chart. Somewhere up here. So then we got to go back to our line, temperature line, and now we got to extrapolate this. So 30, 31, 32, 33, 34, I don't know, 34? Somewhere around there, 34. So I'm going to guess 34. I'm sure that the textbook will give us a much better response because they're actually graphing. When you have a ruler and a graph paper, you'll be able to do this much better, right? Let's see what they got. 35? Okay, so everything we did was the same, right? They used some graphing software. We can use pencil and paper though. It was one of the options. They interpreted the line of best fit. They read across to find the body temperature was about 28. Give me 1 second. And we estimated it was 28.4, so very close. And then they estimated that his body temperature would have been 33, and we estimated 34. So again, very, very close. We'll continue with this lesson after lunch.